Even now it is not treated properly. So anyway, so what von Neumann, so in that sense, and then von Neumann introduced the term, that model I used, where this separation between the two peaks of the wave function, Stern-Gerlach or that model, ultimately the two spatial parts of the wave packet get separated. So they are sufficiently separated so that they are macroscopically distinguishable. Now when usually we make a Stern-Gerlach measurement, we always try that way, that the separation between the peaks of the packets are large compared to the width of the packet individual. So what we mean is that they are in that sense macroscopically distinguishable so that you can distinguish between the two outcomes. So the measurement outcome, so the very notion of a measurement outcome itself contains the notion of realism in the macro sense or classical sense, the way we use. So now, really? In that sense, in the operational sense of
so being, at the end of the day, you can't have the superposition of pointer up and down space.
Yeah.
Otherwise, you're not in a macroscopic.
Yeah.
You're not reproducing macroscopic words, so it can't be sufficient to just have an entangled state.
No, yes, that is the point I'm making. So this part up to this now, but this is what we require, this outcome to have, measurement outcome to have these properties, reality and all this, and the apparatus should be.
Does that depend on the nature of the interaction? Or
No, quantum description can only lead up to this point. The nature of the interaction will not help. So some additions in the standard framework, the story stops here. And then those who dismiss the measurement problem, and there are very illustrious physicists among them and so on, they basically, those who are convinced, they feel it is an obvious point. But those who are not convinced, even very great persons. So I will soon give some representative quotes. So basically what is saying that if the story is this much, and this much what standard quantum mechanics can provide, and von Neumann's, that chapter provides this much. But von Neumann did realize that this is not the whole story, so he introduced the collapse postulate. But his collapse postulate and Dirac's collapse postulate, there is a subtle difference. Dirac referred to only the system, and von Neumann referred to this wave function being collapsed to this term or that. I'm saying this all this because there are students here who want to
had this initial notions of classical realism.
Yes.
So this resembles something.
Yeah, that's
so
why.
We would have had that thought in mind.
That's why I introduced the term classical realism and defined it in that way, which is compatible with what we mean by which we mean by measurement outcome, individual measurement. What we mean by measurement outcome. That notion is taken for granted, the measurement outcome. But honestly, the measurement outcome is what really at the end of the day, some stable, discernible change of some property of the measuring apparatus. Now if you describe measuring apparatus and measured system on the same footing in terms of quantum mechanics, then you cannot go beyond equation 16. No matter how detailed, and many people working on quantum theory of measurement miss this point. Fat books are written, lot of sophisticated mathematical models are built and all this, but at the end of the day, this is what is done. Even approaches like POVM and so on, whatever you do, you have to take on board this fact that no matter what you do, it comes to there, and it's a question. But then I will indicate how very clever people, and they are all very distinguished people, appreciate the problem but tend to bypass it in a very clever way, so that ordinary mortals are misled. So this is it. Because measurement problem comes in different avatars, in different books and different discussions on foundational issues. But I am sticking to more to an operational way, because what you mean by measurement outcome, as I said, the Stern-Gerlach is an archetypal example, and it's a very nice example. Here, it's why I am repeating Stern-Gerlach, because there the particle position is the apparatus meter coordinate itself. Spin is the observed quantity. But that itself is not sufficient to complete the measurement. You need the screen. So you need to include screen in this story. But then if you include screen in this story, even if this is the spin and this is position of the particle and there is some screen detector location and the two wave packets are well separated peaks and so on, still the interaction, if it is described linear unitarily, it will be in another pure state, because a pure state will evolve into a pure state. So it will remain in the entangled form, only there will be some additional term here, the screen detected term in the upper half and the lower half.
Can I
The
ask
two
this?
states.
Suppose someone gave a modified version of quantum mechanics in which it did evolve to a mixed state.
Yeah.
Would you regard that as solving the measurement problem or not?
Yeah, mixed state, modified, if you modify, in fact people have tried the Schrodinger equation to modify it, and I'll come to that point. The collapse, the spontaneous collapse models,
Yes.
those stochastic Kosav collapse models, they modify the Schrodinger equation in a way that this state becomes a mixed state by the fundamental equation.
That's not quite my understanding what they're trying to do. But I just wonder your point of view. Suppose you could, suppose the real theory did modify it to a mixed state.
Yeah.
Wouldn't, in my view, that would still not solve the measurement problem. So I'm asking you whether
No,
or
that
not
is
it
a
would.
necessary ingredient, the mixed state. Because if you remain at the pure state level, then either there are, I'll come to that, the approaches that have been put forward. For example, in Bohm model, the pure state is maintained but changes, add some new ingredient to solve the measurement problem. So one cannot give a straight cut answer to that. It will depend on how you set up your framework. And I will illustrate this.
But in any case, you think it's not sufficient?
Not
just to evolve to a mixed state.
It's not sufficient. That much is clear from. I'll come to some specific examples how people have tried to modify and get. So that will be instructive. But one cannot always give a definite.
Because some people take the point of view that it does suffice. And I've never,
yes,
I've never understood.
Oh, that is again same confusion. So that's why I'm coming
Okay.
to it slowly. And also in that context, it will be instructive to analyze some of the approaches that have been produced who claim to solve the measurement problem by modifying the framework. But some of us believe they are not inadequate. And why they are not adequate is related to what you were saying. So, as I repeatedly asserting that the definite value of a relevant apparatus variable denotes an individual outcome, and different outcomes have to be distinguishable in order that you can verify the measurement statistics. So the final post-measurement ensemble is necessary that it should be heterogeneous. So that even so, this does not achieve the full necessary condition. And no matter how you enlarge this description by including the detector states and so on, and include the interaction between the particle and the screen, or particle and the counter states and so on, even if you add to it, since they will be all described by unitary time evolution, then a pure state will always evolve into a pure state. So there's no way to escape from it. And now, again, in view of the discussions we had this morning and earlier, I'm meaning here the probability in the sense of the frequency interpretation. That is that I should. Then in the frequency interpretation, probabilistic predictions to verify the Bond-Dirac rule require essentially definite and distinguishable outcomes. So, in a nutshell, the quantum measurement paradox is that although quantum mechanics gives us rules for computing the probabilities of various outcomes, the definiteness of a specific outcome as distinguished from other possible outcomes is not ensured in standard quantum mechanics. In other words, you talk about the probability of this thing happening, this eigenvalue to be half and so on, when even the very occurrence of a definite outcome at the end of a single run of an experiment is not ensured. So, as Leggett said, it as if the standard quantum mechanics forbids any measurement to take place. So the event does not take place. There is no scope for something, some outcome being registered. So it's a rather an acute paradox. It's not a matter of just conceptual inadequacy. It's internal inconsistency, because as I in the beginning of my talk, that's why I made this point that Schrodinger equation alone is not sufficient. You need the rule Bond-Dirac. And in order to both to be consistent, it should enable the mathematical framework should enable that at the end of the measurement process, one should be able to verify those probability rules in a consistent way. Now, by consistent way, one means that by ensuring, that is implied automatically, by ensuring the definiteness of individual outcome, that they can be distinguished. Suppose I predict, given some stochastic model, classical and a coin tossing point, that the probability of this half and half, but that theory does not ensure that in a single run, the coin will fall either head or tail. Then what is the meaning in that theory of to that statement of calculating probability to be half? How can it be verified? So it is a contradiction of that kind. So many people who are convinced by measurement problem refer to as an internal inconsistency within quantum theory, in the sense that mathematical formalism, that means Schrodinger equation, is not consistent with Born-Dirac rule. In this sense, that to verify Born-Dirac rule, you need to assume definiteness of an outcome as distinguished from others. So these two properties, definiteness and distinguishability. And it is the point about distinguishability with von Neumann touched upon at that very first exposition of the measurement problem. That is remarkable. That he talked about and he spent few pages on that distinguishability point. So obviously he was not satisfied how to characterize this notion of macroscopic distinguishability within quantum mechanics. And that is a soft spot of quantum mechanics. And in fact, I will make this point a little more dramatic and also empirically relevant in the modern context by giving you an example, because now the acuteness of the quantum measurement problem, one line of study has been that the measuring device, what we mean by the measuring device to be necessarily macroscopic. Nowadays, with the advent of technology and so on, the measuring device can be in the mesoscopic level and so on. So biomolecular analogs of measuring device gives a very instructive example of measurement problem, how acute it is. And I will come to that. But before that, I will say a few words in relation to what Rafael has said about other sources, so that my discussion is complete about the measurement problem itself. This is just repeating those points because this is an important point, and that is incompatible with the point about incompatibility and no description of the process. And also it is important that, so therefore the question such as when a measurement is completed or when an outcome is actualized is left unaddressed. Now this point is important. Now those who follow experimental studies on quantum non-locality, and that is a very buzzword in quantum non-locality experiment, is to have a loophole-free test of Bell's inequality. And one of the loophole is referred to as the locality loophole. So that is that in DPR case, when you make a measurement here, then after the measurement is completed, the light, you have to do the other measurement in a time shorter than the time it takes for the information to travel from this wing to that wing. So when Alan Aspect did his experiment in 1983-84, he originally claimed that, okay, this is clear cut. And then there were criticisms and so on. So I've been working on foundations from this early 80s during the time Alan Aspect. So there has been continuous debate, and in mid-80s and late 80s, Leggett made an important point regarding Alan Aspect's experiment, that when is an experiment completed is a crucial issue in deciding whether your locality loophole is closed or not. Now, people who discuss those loopholes, and even now for many years, locality loophole means I do the measurement here, the photon hits the photomultiplier and some current is produced, the time at which the current is produced. Now the question is whether the production of the current itself is a measurement process complete. Then you have to take the time in which the detector, so you have to properly take into account the time when the measurement is completed to characterize it in order to guarantee that no time is left for that information to travel to the other way. So to properly address the locality loophole, one needs to address this question when a measurement is completed in a clear, unambiguous way. And only in recent years, for the last decade, people who appreciate the quantum measurement problem, like Nicolas Gisa and others, they tried to address this problem, and their famous experiment, GISA experiment 2008-10, can be done with 18 kilometer separation and so on, precisely trying to set up. And then they referred to as locality loophole free experiment in the context of a certain type of collapse model, that is the Penrose collapse model. So in that context, they ensured the 18 kilometer separation. But still, one may say that okay, that is one model. So it is model dependent how you will address the question. I am mentioning this point because if you read that paper, and that work was very well publicized as the locality loophole free test. But in the paper it is written, but nowadays how the papers are written, that point is mentioned but not highlighted, that it is with reference to that measurement model, it is locality loophole free. And when I asked Nicholas last year, he agrees that that is, but with respect, it's essentially, because I was confused because all the discussions refer. So still, so this point is a very vital point, which is conveniently glossed over whenever required, and it's a profound point. So, studying quantum measurement problem, addressing quantum measurement has implications beyond just being conceptual understanding or philosophical understanding. Okay, and often quantum measurement problem, those who believe it to be paradox, refer to it as paradox now. Paradox is a loosely defined term, but here the term paradox is used. This definition of paradox is from the philosopher W.V. Quine. He gave this definition of this issues in philosophy of modern physics. So in this sense, quantum measurement problem is a paradox because you start with the rules of quantum mechanics, they are plausible and all plausible premises. The argument is plausible, the pure state interpretation, mixed state interpretation, and then you come to an implausible conclusion that an experiment has no definite outcome. So in that sense, it's a paradox. And as I have...
You referred to this locality loophole.
Yeah.
How much separation in time would you need so that everyone would agree that the measurement was complete?
Yeah, that is not yet fully objectively defined. That would depend on our
well,
model.
If you, I mean, I think there's some level where everyone would agree.
Yes. And at some level, But at those levels in which everyone will agree, the separation that is required would be larger than, so far the separation at which Bell's inequality has shown that 18 kilometer separation.
I'm asking because there are proposals to do satellite experiments in which you would have, I don't know exactly how much time, that's why we'd have some significant fraction of a second. So I'm wondering how much you think would be needed.
I'm mentioning in that 18 kilometer experiment, the time interval that is involved is of the order of microseconds.
Microseconds. But do you have a sense of what would be, suppose it was milliseconds, would that be enough, or it was 1 second? Would everyone agree then?
I agree. For that, the distance scale that will be the separation scale that will be required with photons.
Yeah.
So with photons, people have done studies. The distance scale is, they claim it of the order of 100 kilometers or so with the kind of photon detector.
That would be enough?
That would be.
So
and Zeilinger's group claim to have done that circumstantially. That's why, in fact, very recently, just maybe.
246 kilometers?
Huh?
Wasn't it more like 200 something kilometers?
Or 200.
Yeah, there was an island and...
That Zeilinger's experiment where he claimed to have closed both the loopholes.
Yes.
The detection loopholes as well as the locality.
Yeah.
There is of that order. But then one has to still, I have not studied that close enough. Anyway, so that
so these satellites,
and what's the
experiments
satellite?
will be well above the threshold.
Yeah.
No one will argue.
No, I'm not saying that locality loophole.
No,
but
I'm
I'm
just
saying that,
curious
that is important. And also what is important, the teleportation, the length scale over which teleportation has been achieved is also remarkable. I think the teleportation has been achieved of some of the order of more than 18 kilometers, the Bell test for that GISA, but GISA group achieved teleportation more than that, much more than. Geneva Lake to banks, they did the cryptography also. So the Geneva lake is quite so these are all spectacular. So in that sense, in the macro limit, the quantum mechanics testing, the macroscopic scale, they are all now very viable experimental studies. So in that context also the measurement problem becomes important, one classical micro, macro boundary and so on. And already I have emphasized these properties of the outcome, and this can be done at any way, the objective reality. So the necessity of this whole question of realism comes because of measurement process and the reality of an outcome which is not ensured by the standard frame. But there is also, this is conceptual problem, and this conceptual problem is also related to another fundamental formal aspect of the conventional framework, because this is referred to as the problem of preferred basis. That also makes quantum measurement problem a rather acute problem. That is, this is a simple way of saying that all, as we study, the different sets of basis states are equivalent. So suppose you have a wave function of this form where psi 1, psi 2 and alpha 1, alpha 2 are the apparatus states corresponding to distinguishable outcomes. Then you can, if it is still a pure state and you follow the rules of quantum mechanics, you can expand it in this form. These two states are orthogonal. By the way, the macroscopic distinguishability, one useful criteria for it is taken in quantum measurement theory to be orthogonality between the two states, implying that the states are distinguishable. So in that sense, you can always expand it in another basis comprising of these two apparatus states where they are also orthogonal, but they are linear combination of the earlier two states. But then psi 1 and psi 2, if they are eigenstates of a dynamical variable A, and then alpha and alpha 2 are the apparatus states, then the same interaction can thus be looked upon as the measurement of an observable whose eigenstates are this and this, and this another dynamical variable B, and one can choose this C1, C2 such that A and B are non-commutative. So in this way one can say that the equivalence between different sets of basis states, if you hear that my description of measurement process stops the best one can do with the usual standard quantum theory, then one can also proceed this way. And as in the famous debate between Hawking and Penrose, when Hawking said, whenever I hear of, she made this famous statement, because he's very dismissive of the measurement problem. And I remember at Tokyo, that conference, Hitachi conference and foundation, Hawking gave a talk and the arguments against quantum measurement problem and all this, and then he said that whenever I hear of Schrödinger's cat, I feel I should look out for a gun, because people worry about a non-existent paradox. So in the Hawking-Penrose debate, that was Penrose's answer. Penrose said that this could be the alive and dead states of a cat, but my quantum mechanics rules permits me to write it in this way, where the cat can be in the superposition of alive and dead state. There are two such possibilities. So an A-B can be non-commutative. So the same measurement interaction can be described as the measurement of two distinct dynamical variables who may not necessarily commute.
Okay, alpha prime, alpha double prime, isn't it a different interaction? Measurement interaction?
No.
Because
it
the
is the same
basis
interaction,
change,
the final state, you can always write it in this. I can, because if my interaction leads to this state,
yes.
then formally this state, and you describe it by a density matrix and ensemble. Yes. So, and this has the same density matrix as this one.
But the measurement would be corresponding to
Your measurement
B,
would be corresponding to
B.
to the dynamical variable B. So the same interaction can be used for measuring both A and B simultaneously. And A and B can be made non-commutative by choosing C1 and C2. So in that sense also you lead to inner contradiction. So that earlier part of the argument I showed about showing quantum measurement problem, even if one is not convinced by that, this is one way of looking at the quantum measurement problem. Why it is a problem and why in quantum theory.
I'm confused. Mathematically, you're assuming you identify you're not quibbling about which is the apparatus and which is the measuring system.
Yes.
So I would have thought that unless C1 equals C2, or there's some sort of degeneracy, that's the Schmidt decomposition.
Schmidt decomposition
Isn't that essentially unique?
Schmidt decomposition, here system and apparatus states are level in the two
Yes.
distinct, and then once you have such a state, then you can always, because the same density matrix, for example, it is an ensemble really, system apparatus, and the same density matrix can have an underlying different wave function decompositions.
It can, but generically it's unique if you demand the different basis states to be orthogonal to each other.
But why should we demand it here?
I don't know.
No, yeah. If you impose
If you
some
demand
extra,
that
yes.
one can do that.
Impose, but yeah. So that will be one way of tackling the measurement problem. And in fact, that is what I will come to. What environment-induced decoherence does is to do that. What? Yeah. I know. Okay, but thanks for that. So. In fact, so the resolution
So
of
just
the
to clarify, so in this counter-argument, one is allowing decomposition into vectors which are not unique, not orthogonal to each other. Is that right?
Yeah,
general.
but no, they are orthogonal. Yeah. Oh, but yes, this is the basis states are not
The
orthogonal.
basis states.
Yeah,
You mean they're not orthogonal, one basis is not orthogonal?
to the other. Not,
So why is that important?
no,
Well, you were telling us that the
No.
microscopically distinct
no,
states should
macroscopically
be-
these two are distinguishable. This alpha 1 and alpha 2 with this property.
Just like
This
the
property
basis
is ensured in that basis. This
I see,
alpha
those
1.
are orthogonal, but
Orthogonal.
the system
System,
states are not
yeah.
orthogonal.
Psi 1 and psi 2 are orthogonal. Similarly, this wave function is orthogonal to this one.
But the
Doesn't that re-
alpha prime and,
Alpha double prime are orthogonal.
but the alpha 1, alpha 2 are not orthogonal.
Now, alpha 1, alpha 2 are
Not
orthogonal.
orthogonal to, either of them is not orthogonal. The two bases are not orthogonal.
Yeah.
That's the point
Fine,
you're
yeah.
making, right?
No, that's not the point. I would have thought you couldn't, maybe this is a diversion, but I would have thought you couldn't do this unless C1 equals C2, or there's some sort of degeneracy.
Oh, C1 equal to C2.
You're claiming that
maybe,
arbitrary
maybe.
C1 is
No,
C2?
yeah, arbitrary. Yeah,
Then we'll have
you are
to-
right,
we'll have
right.
to
In
look at that.
C1 equal to C2, there would be there.
But suppose they're not equal, does this always work?
Yeah. But if they are equal,
C1 equals to C2, then it's technically
C.
Well, maybe
It's not immediately clear from here.
Maybe we should.
But if there has been a theorem that density matrix, when you start with this kind of thing, the decompositions, there is some special property in the case C1, but how that is relevant here, I am not sure. But that's an interesting question. Study this. I remember seeing some discussion about it, because this is important in the general context that the density matrix can have underlying different wave function descriptions and they are equivalent.
It's certainly, if you ask a density matrix, a density matrix can be superpositioned in an infinite number of ways.
Ways.
Zero states. So if you ask the different states to be orthogonal,
Then you have
then
some
generically it's
restrictions.
a unique decomposition.
To what extent it will be unique is maybe one has to see. But it is a requirement. But that would be interesting to see in the case of this two level example. How it occurs.
Sorry, what is the problem? The states are not orthogonal.
Which one?
I still couldn't understand what the issue is. What is Rafael? If C1
Now, Rafael is trying to understand if there is any restriction on this coefficient C1 and C2.
There has to be no
So if C1 was equal to C2, then we
Yeah, yeah, C1, if C1 is equal to C2, then something special happens.
Well, I was thinking that this wouldn't work. I think I just need to look at it.
Yeah, yes,
I was
one
thinking
is-
this would not work unless there was some special
It's a special
relationship
relation.
between C1
C1
and
and
C2.
But in general, this is what.
Well, do you have the, I mean, look at your alpha prime and alpha.
One has C2. So
You're
far as I
saying-
can see C1 equal to C2. Yes, yes, it should still work. Maybe the
Oh,
restriction will be
oh, here you go. These two at the bottom are not orthogonal.
Yeah, unless C1
Unless
equals
C1 equals C2.
C2, yeah.
So the statement is you use orthogonal states for the apparatus,
Apparently, but
but the states for the system are not.
But, no, but because
orthogonal.
it's an eigenstates, I say, if they have to be looked upon as an eigenstates of another dynamical variable, they need to be orthogonal.
Then they need, so in this case, it
Yeah,
cannot be
yeah,
like.